Welcome. This course is organized around 7 conceptual units. Together, they provide a progression from the foundations of natural language processing to more applied systems that use language models, retrieval, and web data. In this opening lecture, I will first give you the overall roadmap, and then we will begin with the basic concepts and use cases that motivate the rest of the course. We begin with a short introduction to natural language processing, what NLP is, what it is used for, and what current systems can do. We will also look at a few pre-trained models in action. The goal there is not to analyze every line of code immediately, but to build intuition for what these tools make possible. After that, we move into classification and sentiment analysis. Many of you already have a background in data analysis, so the core ideas should feel familiar. We want to classify text or speech, for example, by estimating whether the sentiment is positive, negative, neutral, or mixed. The next topic is text summarization. We will compare different techniques and models for reducing longer text into shorter, useful summaries. Then we will study information retrieval with the longer-term goal of building RAG systems. RAG stands for Retrieval Augmented Generation. These systems use external information that we retrieve from documents, databases, or websites, and then use that information to answer questions. That naturally leads us into web scraping. To build a RAG system, we need data. In the best case, data is available through an API. But sometimes there is no API, or the API is too expensive or too limited. In those cases, web scraping can be one possible way to collect data. We will also study prompt engineering. No matter which model you use, you need to communicate your tasks clearly. Prompting is about shaping the model's output by specifying what you want, what format you expect, and what constraints matter. Best practices change quickly, so we will focus on durable principles and also look at bad examples because poor prompting patterns remain useful to recognize. Finally, we will discuss recent developments in LLMs and LLM applications. The course then concludes with an overview. For now, the important point is the structure. We will move from concepts to tools to applications and then to more complete systems. With that overview in place, we can move into the substantive part of the lecture. We will begin with conceptual grounding and then shift into practical examples. Keep the course arc in mind. Each topic adds one capability that we need for the final, more applied systems. Let us begin with the basic definition. Natural language processing, or NLP, is a subfield of artificial intelligence concerned with enabling computers to understand, interpret, process, and generate human language. It combines ideas from linguistics, computer science, statistics, and machine learning. The central goal is to reduce the gap between how humans communicate and how machines represent information. It is useful to place NLP inside the broader AI landscape. Artificial intelligence is the broadest category. It refers to systems that attempt to perform tasks associated with human intelligence. That is reasoning, perception, decision-making, planning, and language understanding. Machine learning is a subset of AI. Instead of programming every rule by hand, we train models to learn patterns from data. For example, in fraud detection, a model might learn from historical transactions which combinations of signals are associated with suspicious behavior. Deep learning is a subset of machine learning. It uses neural networks with multiple layers, which is why we call these models deep. These layered architectures are especially powerful for high-dimensional data such as images, speech, and text. NLP intersects with both machine learning and deep learning. On the machine learning side, NLP includes tasks such as text classification, sentiment analysis, and named entity recognition, or NER. These tasks can be solved with classical supervised or unsupervised algorithms such as logistic regression, support vector machines, decision trees, or clustering. At the same time, model NLP is heavily shaped by deep learning. State-of-the-art language systems often use neural architectures, especially transformer-based models. GPT is the most familiar example. GPT stands for Generative Pre-trained Transformer. The name tells us three important things. It generates text, it is pre-trained on large datasets, and it is based on the transformer architecture. Two terms are worth clarifying immediately. The first is transformer. A transformer is a neural network architecture designed to process sequences such as sentences or documents much more efficiently than many older architectures. Before transformers, common approaches included recurrent neural networks or RNNs and long short-term memory networks or LSTMs. Those models were important, but transformers became the major breakthrough because they handled context at scale much more effectively. The second term is GPT itself. A GPT model is a particular kind of transformer model trained to generate human-like text from a prompt. Training these models requires enormous datasets and substantial computing resources, which is one reason large commercial models are expensive to build and operate. Today, the more durable way to describe this is to talk about frontier GPT models and multimodal language models more generally. OpenAI's current documentation, for example, presents GPT 5.5 as the recommended starting point for complex reasoning and coding, while smaller GPT-5 variants are useful when latency and cost matter. The important conceptual shift is not a single product name. It is that current language systems increasingly work across modalities. They can process text and image input, and in audio-oriented interfaces, they can support speech-to-text, text-to-speech, or real-time voice interaction. These terminology can sound dense at first, but the hierarchy is straightforward. AI is the broad field. Machine learning is one way to build AI systems from data. Deep learning is a powerful family of machine learning methods based on layered neural networks. NLP is the language-focused application area that can use both classical machine learning and modern deep learning. When we later compare models or build prototypes, these hierarchy will help us keep the concept separate. For the rest of this lecture, do not worry about deriving the transformer architecture mathematically. The goal today is to understand what these systems are used for, what kinds of workflows they enable, and what basic pre-processing steps are needed before we can work seriously with text data. That gives us the basic vocabulary: AI, machine learning, deep learning, transformers, GPT, and multimodal language models. Now let us make the idea more concrete by looking at where NLP already appears in everyday life. The first examples are personal assistants: Siri, Alexa, and Google Assistant. These systems use NLP to interpret spoken requests, map them to actions, and generate responses. More recently, systems such as ChatGPT, Claude, Gemini, and other chatbots have made conversational interfaces much more visible. Customer support is another major example. Tools such as Zendesk and chatbot platforms are used to answer common questions, route tickets, identify customer intent, and escalate difficult cases to human agents. This is not only about replacing a human response. Often it is about triage, prioritization, and faster access to the right information. Machine translation is another well-established area. Google Translate and DeepL are familiar examples. Translation systems have improved dramatically because modern models can represent meaning across languages rather than simply substituting words one by one. Sentiment analysis is widely used in social media monitoring, customer feedback analysis, brand tracking, and market research. The goal is to estimate the emotional orientation of text. For example, whether a review is positive, negative, neutral, frustrated, enthusiastic, or mixed. Email filtering is also NLP. Spam detection in Gmail and similar systems has become so effective that most users rarely see the amount of spam being filtered in the background. The system is classifying incoming text, learning patterns, and continuously adapting. Text summarization has become increasingly common as well. Microsoft Teams and Zoom can generate meeting summaries from transcripts. Those summaries are produced by NLP systems that identify main topics, decisions, and action items. Search engines also rely heavily on NLP. Modern search results are not just lists of pages ranked by keyword matches. Search systems interpret queries, estimate user intent, summarize content, and often generate direct answers before the user even opens a link. Speech to text, often abbreviated STT, converts spoken language into written text. Lecture transcripts, meeting captions, and dictation tools all use this technology. The reverse direction is text-to-speech, or TTS. TTS systems convert written text into spoken audio, and some modern models produce voices that are increasingly natural. So why does this matter? Imagine computers could not process human language. Systems such as Siri, Google Translate, automated email triage, customer support bots, meeting summaries, and conversational search would either disappear or become extremely limited. NLP is what makes natural interaction between humans and computers possible. The impact is not limited to consumer tools. In healthcare, enormous amount of information exists as unstructured text. Patient notes, research articles, clinical trial reports, and medical records. NLP can help identify symptoms, diagnosis, medications, treatments, and risk factors in those documents. Tools in this space can support predictive analytics, personalized care, and medical research workflows, provided they are used with appropriate caution and oversight. Notice that all of these examples involve the same underlying move. Language becomes data that the computer can search, classify, summarize, or transform. The input may be a spoken request, a meeting transcript, a customer message, a medical note, or a search query. The output may be an answer, a label, a summary, a translation, or a structured record. Once you see that pattern, many NLP applications start to look less mysterious. Research is another area where NLP is valuable. The volume of scientific publications is now too large for any individual researcher to track manually. NLP systems can help summarize papers, compare findings, extract claims, and synthesize results across studies. In clinical research, this can also support the analysis of trial reports and medical literature. Speech-to-text transcription of doctor-patient interactions is becoming more common as well, although privacy, consent, and accuracy remain critical concerns. In finance, where large text-heavy datasets are common, NLP is used to organize and interpret information from news articles, financial reports, regulatory filings, emails, call transcripts, and social media. These systems can support sentiment tracking, risk analysis, anti-money laundering workflows, fraud detection, and market monitoring. For example, a model might analyze news and social media to identify a change in market sentiment or scan regulatory filings for signals that indicate potential financial risk. Customer support is another high-impact setting. Large organizations receive millions of customer questions, and customers expect fast, accurate, personalized responses. NLP systems can classify incoming requests, detect intent, retrieve relevant FAQ entries, route tickets to the right team, support multiple languages, and decide when a case should be escalated. Tools such as Zendesk and related platforms use these techniques to make support workflows more efficient. It is useful to pause here and think about your own domains. Where is there a large volume of language data? Where do people spend time reading, summarizing, routing, translating, comparing, or extracting information? Those are the places where NLP may improve efficiency. One example is marketing. Teams can use NLP to draft or classify client emails, summarize campaign performance reports, analyze comments, monitor brand sentiment, and automate parts of reporting. The point is not that a model replaces all human judgment. The point is that it can reduce the amount of repetitive language work and help humans focus on interpretation and decision making. Another example comes from public administration. Many government services are underused because citizens do not know they are eligible for them, or because eligibility information is buried in administrative documents. NLP can be part of a larger pipeline that extracts entities, relationships, and eligibility rules from public records. Those extracted elements can then be represented in structured format such as knowledge graphs. This is closely related to RAG architectures, where retrieved information is used to answer user questions. Education is also a natural application area. Learning systems could adapt to a student's skill level, pace, questions, and misunderstandings. Text comments, quiz, responses, or discussion posts could be analyzed to identify where students are struggling. In principle, this makes more personalized instruction possible. In practice, it also requires careful design because education is not only an optimization problem. Still, it is a useful example of how language data can support better feedback and better learning experiences. The general pattern is the same across domains. NLP helps convert unstructured language into information that can be searched, classified, summarized, retrieved, and acted upon. This conversion is the key business value. Organizations already have large amounts of language data, but much of it is locked inside documents, messages, tickets, and transcripts. NLP does not make the data perfect, and it does not remove the need for domain expertise, but it can make the information easier to access and easier to process at scale.